Welcome to Mrs. Mahoney's podcast. This is our first one in Unit 8, which is all about stoichiometry. Now, it's Unit 8 packet, but I just want to let you know in the book, this is Chapter 12. And again, don't forget that book is a great resource, an additional resource. You don't understand something, it's a question, you have a week, it's the weekend, it's the night. Go back, look through that book also. Replay the podcast, or you can go through the book to explain some things. Okay, now in your packet, that first page, I told you after the test, that to me is just review. I think you should be able to use old information. That's finding molar masses, using your periodic table, and just doing some mole calculations. So I'm starting on the next page, and so if we number our page, I am numbering the cover as number 1, so I'm on the third page. We're going to start looking at some stoichiometry. I want you to have a periodic table out and also to have a calculator, because as I'm going through these, it really, to get the most out of it, to have a calculator in your hand to understand where I'm getting these numbers instead of just blindly copying me down. I need you to crunch them, not punch them, that's punch them and crunch them, to figure out where they actually came from. That's how you're going to learn. Again, by practicing is how you learn. So what is this long word even mean? What we're looking at right now is really technically reaction stoichiometry. And we're just going to start comparing mass relationships between reactants and products in a chemical reaction. So right here at the top of page 3. Okay, now sometimes we can say a product to product or a reactant to reactant. If I have blank grams of hydrogen, how much oxygen would I need to make water? So that's the whole thing, is we're using it with a balanced equation. Okay, so first let's just go to a basic analogy. And you'll hear me say again and again that the balanced equation is our recipe. Well, here's another recipe. And I hope you've eaten dinner. Depends on when you're doing this podcast, because this will probably make you hungry. This is a bacon double burger. Now, I have talked a little bit with my son, about 6'2", during football. He was about 260. He liked them big. So a hamburger bun, 2 hamburger patties, 4 slices of cheese, and 2 slices of cheese and 4 strips of bacon. Okay, so this is what you kind of look at. If I had 5 bacon double cheeseburgers, how many hamburger patties would I need? Well, you're looking at this. Well, what do I need? And this is where we're going to start writing it. Well, I want 5, well, let me see, BDs. I'm going to call them bacon double cheeseburgers. And I want to know, okay, how many hamburger patties do I need? Well, for every 1 bacon double cheeseburger, oops, that should be a double, I need 2 hamburger patties. And that would be 10 total. Probably most of you are going, duh, Mrs. Mahoney, I could see that in my head. But what I want you to know, this is the new step that we're going to be using. This is just my ratio that I used in this hamburger analogy, that I know that for every 1 hamburger, I need 2 patties. So if I asked you how many strips of bacon, then you could say, well, for every 5, I know this would be what, 4 to 1. So 5 times 4, it would be, what is that, 20. Well, let's go backwards. What if I have 28 strips of bacon? So now I'm looking at bacon. How many cheeseburgers could I make? Well, same thing. What is my ratio? For every 1 bacon double cheeseburger, I need 4 strips of bacon. So now 28 divided by 4, we're not going to be able to make a full one, will we? Yes, we can, if I could do my math. What is that? That's actually, 7 bacon double cheeseburgers. I did pick an easy number for a reason. Okay, all of this, these steps are the same steps we're going to be using, but instead of using hamburger buns and something you're really comfortable with, we're going to be using our balanced equation. This right here is called a mole ratio. So this is our next definition, kind of looking at words you're going to be using a lot. And these are the questions that show up on the CAs and in the EOCs. What is that mole ratio? It's just a conversion factor that relates the amounts, and here's the key, in moles of any 2 substances involved in a chemical reaction. Okay, so you might say, where does this magic mole ratio come from? It comes from something you're very, very familiar with. And in fact, so I would add this when you say, where does this come from? It comes from the balanced equation. more specifically, the coefficients from a balanced equation. So here's, again, my favorite reaction, definitely during stoichiometry. So what is this saying? Okay, we know this is assumed of a 1. Okay, when I'm looking at this, this is telling me 1 mole of nitrogen plus 3 moles of hydrogen will give me 2 moles of ammonia. If it was a recipe, we could have said 1 cup of nitrogen plus 3 cups of hydrogen will give me 2 cups of ammonia. Well, we don't use cups, we use moles. That's why it's 1 mole of nitrogen to every 3 moles of hydrogen will yields 2 moles of ammonia. So possible mole ratios in, looking at this, you're just comparing them. So for every 1 mole of nitrogen, I need 3 moles of hydrogen. That's what this one is saying. Look at this one. It's telling me I can reverse it. Well, for every 3 moles of hydrogen, I can use 1 mole of nitrogen. Just like the bacon analogy, I'm just going to flip it to however I need it. And again, what I want goes on top. So what you want goes on top. What you have is on the bottom. Well, this one I would use if I wanted to know how much ammonia I have, if I know I have a specific amount of hydrogen. Okay, there's many more. I could flip this. I could compare nitrogen to ammonia. So you have many possible mole ratios from the one balanced equation. So the last little vocab to be writing, the last vocab is called the theoretical yield. That's what you're calculating. So it's the calculated amount of yield, the calculated amount of, how about if we change this, product produced. So not yield. The yield is the calculated amount of product produced. It's in theory. If I have 100% of my reactants becoming 100% of the products, this is how much I would get. Kind of call it the it's the pencil one. So it's the one I can sit down and do the math. It's the calculated one. We're going to use this down the line as a guide because we'll say, okay, if I'm going to get out 20 grams, but I only got 15 grams, how well did I do? So this is what we're going to be using in a couple of days. So when it says theoretical yield, you're like, where is that? This is everything that you've been calculating. So when you calculate a product, you are calculating the theoretical yield. So the last thing to write down, and again, I've said this, but make sure you write it, you have to have a balanced equation to write it. To solve it. You need that balanced equation to solve the stoichiometry. Let's just start practicing some of these. So let's just start practicing some of these. And so we're right here, okay, all these first ones. Look at what I have written right here. These are when I'm given mole of A to mole of B. Okay, these A and B's are what you substitute in for anything. A is what you are given, B is what you want. So let's look at this product. How many moles of potassium carbonate are needed to produce 15 moles of carbon dioxide? So in this case, if I'm doing this, this is what I'm given. So this is my A, carbon dioxide is my A. What am I looking for? Potassium carbonate would be my B when I'm looking at this steps. This is a one step. So I write down, always again, just like when we were doing mole, what I know. Well, I know I have 15 moles of CO2. Okay, now some of you might think, okay, I am not going to go to that work and write down all my compounds and do all this. Yeah, you are, because this is showing your work. The other reason is it keeps your mind straight. And it keeps you from making silly mistakes. So when I say that, okay, I need my mole ratio. Looking at my balance equation, I check that it's balanced. 2 potassium, 3 oxygen, 1 carbon. Okay, we're starting easy. This one is. But I'm still going to write it down as I would see it. If I give you an easy one and it's on a quiz, you still write it down. If it's on a multiple choice, then you don't have to do that. But I write down, what do I want? Well, I know that I get out 1 mole. I need of potassium carbonate, 1 mole for every 1 mole of CO2. So hopefully even by looking at these when your multiple choices do come, you can see that this is a 1 to 1 to 1. They're the same amount. So if I have 15 moles of this, I am going to get 15 moles of this. If I have 2 moles of this, I'll need 2 moles of this and 2 moles of this. That's what the ratio is telling me. My balanced equation is telling me. So what do I know? Well, I do get out 15 moles. This is reactant, so I need 15 moles of potassium carbonate. Okay, well, let's look at this one. First thing, let's go back and make sure that it's balanced. So I need 2 there, 2 there. So this isn't necessarily all going to be a 1-to-1. So I write down again, this is what I'm given. I have 5.5 moles of hydrogen. What do I want to know? Okay, this is the other thing I'd underline or highlight. I want to know how many moles of water. So start with what I know. I have 5.5 moles of hydrogen. Okay, then I'm going to set up my ratio. What do I want? Water, and this is, some of you might like writing it like this. Water to hydrogen. Again, notice when we write these, remember, they have to cancel out. So that's why I take the time to write this. If I just wrote moles, I want to know moles of what? When I write the moles of hydrogen, that's how I know that the ratio for hydrogen goes on the bottom, water goes on top. So what do I know? Well, I know that I have 2 moles for every 2 moles. Well, mathematically, 2 to 2, you're right, I'm going to still get out the same number, but I can show you how I know I'm going to still get out 2.2 moles of water. Okay, well, let's look at this same reaction. So again, we know to balance it. But this time, look at the difference. This time I gave you oxygen, and I still want to know water. So if I have 5.55 moles of oxygen, this time, how's your mole ratio different? Well, I still want water, but this time I'm giving you oxygen. I have oxygen. So from your balanced equation, what do I know? This is where this is coming from. Well, I know I have 2 moles of water for, look at right here, and again, we assume we know this is a 1, so for every 1 mole of oxygen. So in the math, again, what is it saying? It says take 55.5 times 2 divided by 1. Well, 55.5 times 2 divided by 1 is 11.1 moles of water. Okay, I'm going to leave you number 4 to do, and this is something we're going to be starting with on Monday, going over these that I'm leaving you a couple to try. Okay, well, let's look at some of the different ones. How are they going to be that easy? Are they all going to be that easy? No, sorry. Because the reason, let's look at it, moles don't do me a lot of good in the lab. I have a really, really hard time going back and measuring a mole. So we're going to have to get into the grams. Well, this one, if you notice, is a 3-step because I'm still giving the products in moles. So we're going to have to change it from moles of A to moles of B. That's what we just did. But then once I change them to this mole of this new substance, we're going to go to grams. Okay, how am I doing this? This is what we just used, the molar mass. So let's look at what I have. I have magnesium reacting with oxygen. Okay, first I'm going to write down the molar masses. So I'm going to write down, okay, what do I need? Well, I have magnesium, so I know I'm going from magnesium. Now sometimes when I'm writing these and I start doing, I write what I know right underneath it. So I have this many moles of magnesium. Where am I going? I want to know how much oxygen do I have. How much oxygen? That's my unknown. Also writing it like that keeps it straight. Okay, but what do I know? I'm going to need oxygen. The molar mass of oxygen is 32 grams per mole because it's O2. Well, let's just start with what I know. I have 6 moles, and it's what? Of magnesium. So what do I need to do? I need to figure out how many moles of oxygen from that. Well, 1 mole of oxygen, I'll need 2 moles of magnesium. Excuse me, this isn't oxygen. This is how you can catch your mistakes. So what do? Magnesium. Okay, so that changes it from moles to oxygen. Now though it asks for grams. I want grams, so grams goes on top. Well, what do I know about oxygen? And this is why I write this down, because I need to know the molar mass of oxygen. I don't care about magnesium. I'm done with magnesium. It's now oxygen. Well, 1 mole of oxygen has a molar mass of 32 grams. Now I'm ready to take out my calculator. 6 divided by 2 times 32. And that's how we get 96 grams of oxygen produced. No, excuse me, needed to react it. That's so if I wanted to react all the that magnesium, I would need 96 grams. Okay, let's try one more. So what do I have? Moles of chlorine, and I want to go to grams of sodium chloride. Well, I know I'm going to need the molar mass of sodium chloride. So when I write this down, so I'm putting this down right now so that you know where these numbers come from. That's the molar mass of sodium chloride. So again, I'm going to write down, what do I know? Well, I have 1.33 moles of chlorine. Where do I want to go? This is my unknown. I want to go to sodium chloride. So what's my ratio? That I have 2 moles of sodium chloride for every 1 mole of chlorine used. The last part, how many grams is that? Well, 1 mole of sodium chloride I know has a molar mass of 58.5 grams. So when I do all of that math, 1.33 times 2 times 58.5 in 3 significant figures, I get 156 grams of sodium chloride. Okay, we're going to just do a few more because let's face it, this is still kind of not really worth it to me in the lab because I have that mold kind of still in there. So where we're probably going to see a lot of them, and especially when we start doing labs, this is what we're going to be seeing. These are the longer ones, but these are actually the more practical because really I'm going to give you a gram. So first, any grams I'm given, grams are worthless. You have to get them to moles. So you're going to use right here, this would be the molar mass, but it's of substance A. This right here, how do I do this step? This is where you use the mole ratio. And then how do I do this step? This is where I would use the molar mass of now your substance B. Okay, so let's look at this. First thing I'm going to do before I forget, I'm going to balance it. So I know 3 and a 4, so 6 plus 4, it's 10. That's my 5. Okay, so what did I give you? I gave you propane, and I want to go to carbon dioxide. I gave you grams of propane, and I'm going to go to grams of carbon dioxide. So I'm just going to, over here, just kind of write down the molar masses I'm going to need before I get started. I know I'm going to need the propane. Now this is where, okay, significant figures, again, those sticky little things. I'm going to just pretty much pull molar masses to kind of match what I'm given. So since this has four significant figures, I'm going to go ahead and use a molar mass to 4 significant figures because I would never ever use that molar mass to determine the number of significant figures. Okay, so that's C3H8. Okay, what's the molar mass of CO2? Well, 12 plus your 16 times 2, 44.01. Okay, I don't like this example. I'm sorry, they just happen. This is like a coincidence that these both have very, very similar, almost the same molar masses. That's not always going to be. Not at all, not at all, not at all. Okay, and I'm really sorry if that's going to confuse you the first time. It's just, but this is why I wrote this down. They both just happen to have similar molar masses. Okay, what am I going to start with? My propane. Notice I started a little further over, a little bit more steps. Okay, this is of the propane. Okay, grams, they don't do me good. I need to figure out how many moles that is. Well, 1 mole of propane has a molar mass, 44.08 grams. Okay, next step. Get it from moles of propane to carbon dioxide. Well, from my balanced equation, I know that I get 3 moles of carbon dioxide for every 1 mole I use. Okay, so now we've just changed it to moles of carbon dioxide. I'm right here in my step. I've just changed it to moles of B. Okay, what's the last step? Moles are worthless. I don't understand that. Tell me how many grams. Grams I can visualize. Grams I know. So 1 mole, that's a 1, of CO2. Right here is its molar mass. 44.01 grams. Now I'm going to pull out my calculator. So I'd say 60.03 divided by 44.08 times 3 times 44.01. And to 4 significant figures, I would have 179.8 grams of carbon dioxide produced. So this is telling me for every 60 grams of propane I burn, I'm going to produce 179.8 grams of carbon dioxide. When we talk about combustion reactions, greenhouse gases, this is what they worry about because look at the amount of carbon dioxide that is produced in these combustion reactions. Okay, let's do one more. Again, oh wow, man, look at how this reaction keeps showing up. Hint, hint. I like this reaction. Hint, hint. Okay, so what do I have? Well, I know I have ammonia, 15 grams of ammonia. I want to know how much hydrogen will I need to produce that much ammonia. Okay, first thing I need to do, balanced equation. So I'm going to have a 2 here, and then I'll have that 3 there. Okay, what molar masses am I going to use? NH3, what is that molar mass? And I'm really only going to do it to 3 significant figures because that's what it gave me. And what else will I need? I'll need some hydrogen's molar mass. Okay, now it will get that you don't have to always show me where you get these molar masses. You can just write them right here in this step. But again, I'm trying to show you as much as possible so that you don't think these numbers are just magically appearing. They're appearing because that's the molar mass. And I don't like when you think numbers are just appearing, that I know something you don't know. And look what I just did because I was talking. Okay, let's fix this. I don't have hydrogen. So it wasn't hydrogen that we had after all, was it? It was ammonia. So this should be the ammonia. And what do I have to do first? Grams are worthless. I need to change grams to moles. So it's of ammonia, so I need the molar mass of ammonia. So every 1 mole of ammonia has a molar mass of 17 grams. Okay, then I need to get 2 moles of hydrogen. So this is from that balanced equation. How much hydrogen? Well, we need 3 moles of hydrogen for every what? 2 moles of NH3, ammonia. Okay, last step, what do I have to do? Get to grams of hydrogen using molar mass of hydrogen. So for every 1 mole of hydrogen, it has a molar mass, right? It is actually 2.02 grams. Okay, now when we get the calculator, this is where you just have to make sure you do at every step. So 15, okay, divided by 17 times 3 divided by 2 times 2.02, and what do you get? 2.67 grams. Okay, the last two, 9 and 10, I want you to try, and that's again where we're going to kind of start on Monday. Have a good weekend. Have a good night whenever you're watching this. Monday morning. Anyway, I will see you Monday morning.